Hello. So today we'll actually talk about my favorite number, I to the I, or you can write it as I to the I if you want, which is actually equivalent to 0.20788 and so on. Yeah, it actually goes on there, but the nice thing about this is that it is composed of raising a complex number to another complex number, but it turns out to be a real number. Okay, and so that's why I find that so fascinating. So when people will ask me, "Oh, what's your favorite number?" I say I to the I, and they're like, "Oh, what?" And then I get to explain to them elementary complex numbers. All right, and this is actually very straightforward once you are aware of the so-called Euler Identity, I believe it's called, but basically the relationship between the exponential and the trigonometric functions cosine and sine, because here, so what we want is you want to raise I to the I. So first, we want to find a way to write I, the complex number I, which we know, of course, if you haven't heard of complex numbers before, basically by definition, I squared is -1, or I is the square root of -1. Okay, so we can write I as, so note that you have an I as a coefficient of sine, so we can find a value for theta such that sine of theta is 1 and the cosine of theta is 0. Cosine vanishes, and of course that happens when theta is pi over 2. So we see that e to the I pi over 2, okay, is equal to cosine pi over 2, which is 0, plus I sine pi over 2, which is 1. So that's why I will remain there. And of course, the next step should be obvious. You raise this to the I, you get e to the I pi over 2 raised to the I. Of course, that will just multiply I times I. This will become e to the minus pi over 2. Okay, which of course, if you evaluate, let's see that here. If you evaluate, let me see, I to the I, it's that number, and if you compare it with e to the minus pi over 2, it's also that number. So basically they're equivalent. So that's basically how you define that. Of course, this famous identity is also the one responsible for the very famous e to the I pi. When you let theta equals pi, of course cos of pi is -1, sine of pi is 0, and this gives you e to the I pi plus 1 is equal to 0. So most people say that this is their favorite equation, because it relates very basic quantities 1 and 0, and then two constants e and pi, and then the complex number. Yeah, it really looks beautiful, but from there, from the Euler identity, you can get my favorite number, I to the I. Okay, but so that's my favorite number, but the video doesn't end here, because what I'd like to talk about is, I would like to talk to you about the properties of complex numbers when we plot them using the so-called Argand diagram, because typically what we do is, when we represent, or we want to draw these complex numbers, we plot them in an Argand diagram. So let me draw this one here if I can. Okay, so we have there a diagram, and basically the y-axis, okay, this represents the imaginary axis. Okay, let me just disable the grid. Okay, so this is the imaginary axis, and this is the real. Okay, so the real, these are the typical numbers that we know, 3.5, -4, and so on. Okay, but when you involve I, so you get a combination of real and imaginary numbers, which we call complex numbers. Okay, so for example, the complex number, the complex number 3. So 3 is a complex number, but it is just real because it doesn't have a imaginary component. Okay, so we plot it there. If you want to plot, for example, 3i, so since this is the imaginary axis, the y-axis, this point right here is actually your 3i, okay? But we can also think of these points and look at their distance from the origin. For example, this arrow, you can think of this arrow as representing your number 3, and this arrow as representing your number 3i, right? And the curious thing is that if you look at it carefully, 3, after you multiplied it by I, it actually performs a 90 degrees rotation, what they call this, counterclockwise, okay? And so geometrically, what it means to multiply a number by I is rotating it counterclockwise. So for example, if you have, what if 3i, we multiply it by I, right? So 3i, we multiply it by I. So according to our geometric interpretation, this whole arrow here will rotate counterclockwise 90 degrees, okay? And it should go somewhere here. So in other words, it becomes the number -3, okay? So it's supposed to be -3. And in fact, that's actually where we got our definition for I squared, which is -1, right? So our I squared is equal to -1 because of that geometric interpretation of the rotation, all right? So in general, if you have a number, let's sample, so let me clear my screen first, but in general, you can't, because what I'm showing you are just like pure imaginary or pure real, but what we can do is, we can, for example, consider combinations of real and imaginary numbers. So let me see here, let's say 3i plus 4, for example. So this one, okay? So this number is 4 plus 3i, okay? And it's represented with respect to the origin by this arrow. So the claim is, when you multiply this by I, it rotates this arrow 90 degrees counterclockwise. So let's see that. If you multiply it by I, it becomes 4i. So 4i is somewhere here. And then 3i multiplied by I is, like we said, -3. So that is somewhere over here. So this number is supposedly 4i minus 3. And in fact, if you look at this arrow, if like I'm drawing it very perfectly, you see that that is indeed a 90 degrees rotation. But note that these things are, this is when the reference point is at the origin. So what we can do in general is, we can try rotating different points on the Argand diagram. For example, this thing here, let's say this point is 1 plus I, and then we have another point here which is 1 plus 2i, okay? So we're interested with this arrow. So this arrow it's not anymore with respect to the origin, it's with respect to 1 plus 2i, okay? The sort of length of that arrow, okay, if you think about it, is equal to the difference of the final point, 1 plus 2i subtracted by the initial point, which is 1 plus I, and obviously that is equal to I, okay? So what that means geometrically is, actually this arrow right here behaves just like your I arrow, which is this one, okay? So sometimes we say that these two, they are the same vectors. So what happens if you rotate this, okay, which we know has length I? So when you rotate this I, this vector here, what it does is, it goes to -1. Like we said, rotating it 90 degrees counterclockwise, you multiply it by I, so it goes to -1. But note that this arrow here, it doesn't go to -1, okay? It goes to this point here. So how do we recover that? So the thing is, this one, this arrow, which is I, you multiply it by I, it went to -1. That's with respect to 0. So what we do here is, this is the length of the vector I. After multiplying it by I for rotation, you add the original position, which is its reference point. So this is 1 plus I. That actually gives you, so I times I is -1 plus 1 is just equal to I. So in other words, this, if I rotate it counterclockwise 90 degrees, or I multiply it by I, this distance, it goes here and it goes to the point I. Okay, so numbers, any arrow with respect to the origin, if you want to rotate it counterclockwise, you just multiply it by I, or negative I if you want it clockwise, obviously. But any arbitrary number, a plus bi, an arrow between a plus bi and let's say c plus di, okay, what you do is you take the difference, you rotate the difference by multiplying it by I or minus I, depending on which direction you want it to rotate. Then you add the reference point. Okay, so that should give you the rotation, the new location of the rotation. Okay, so why am I telling you this? So most people will say, in itself, if you're really a hardcore mathematician or a physicist, in itself, this is already very cool. But some people is like, why do I need to know that? Like, what's the use? Okay, so there are some of us that you don't need to motivate it. Once they've seen this, they'll be like, they're like, oh, that is so cool. But there are some people that you really need to show them where it is used. Okay, so of course you can tell them, it's used in solving advanced problems in physics, in like complex analysis or complex calculus. When you do contour integration, it's used in electrical engineering and so on. Okay, but let me show a simpler example, an interesting example where indeed we can apply this as an application. Okay, so let me take a snapshot. This one is a sort of what they call this, a note, a treasure clue. Okay, and this example is by the great physicist George Gamow. Let me take a picture of that, this example here, right? So this is a very curious note, okay, that is found, that is supposed to point to a vast amounts of treasure. And of course, people who want application, that's really what they want. You know, they want to make money of your, how do I make money out of that mathematical discovery? So let's show them. So let me rotate it first so it will look a little bit legit, like a note, like that, like so. Okay, that's it. So let me read the clue. Okay, so according to this note that was left, and then I copied it. It says, go to 77.7 north latitude. Of course, I just invented that number 777. Usually in video games they mean like treasures, but anyway. And 77.7 west longitude, where thou wilt find a deserted island. There lieth a large meadow on the north shore of the island, where standeth a lonely oak. I didn't know trees could be lonely, but anyway, and a lonely pine. So basically it means they're alone, right? It doesn't mean that they're sad. There thou wilt see also an old gallows, so where you hang people, on which we once hanged traitors, right? So that's a gallows. Start thou from the gallows and walk to the oak, counting thy steps. Okay? At the oak, thou must turn right by a right angle and take the same number of steps. Put here a spike in the ground. Now, must thou return to the gallows and walk to the pine, counting thy steps. At the pine, thou must turn left by a right angle, and see that thou takest the same number of steps, and put another spike into the ground. Dig halfway between the spikes, the treasure is there. Okay, so basically what the note says, if you followed it, is there's an oak. So let me change my ball pen to black now. Let's say there's an oak, so let's put a letter O there. Then let's somewhere here there's a pine, okay? And then somewhere in the island there's supposed to be a gallows. Let's put it here, gallows, right? So the instruction is, starting from the gallows, you walk towards the oak tree, okay, going there. You count the number of steps. So let's say this is like, I don't know, 6 steps, let's say. Okay, so what you do is you walk in this direction, turn right. Okay, so after turning right 90 degrees, you will go in that direction again and walk exactly the same number of steps. So in other words, this should also be 6 steps, right? And then go back to the gallows. So after doing this, you put a marker here, a spike. So let's call it spike number 1. Okay, go back to the gallows, walk going to the pine. So let's say, I don't know, let's say this is 3 steps, let's say this length right here, and then turn left. So let me see, when you turn left, you go in this direction, right? 90 degrees, exactly the same number of steps. That means this is also 3 steps, right? Then put another spike. So this is S2. So now it says that you draw a line between S1 and S2, somewhere in between. So let's say, I don't know, somewhere here in between S1 and S2, you dig, you should find the treasure. Okay, so that should be a simple instruction to anyone. But here's the twist. Okay, what if when you go there, you see the oak, you see the pine tree, but the gallows is not there anymore, right? Because, you know, oak and pine trees, they last a long time, but the gallows, it's not alive, it's not a living thing, it rots, right? So what if it's not there anymore? So in fact, the story goes that someone went there, but he has these instructions, but then the gallows is nowhere to be found, right? And so what he did is, in his frustration, he dug everywhere in the island randomly, hoping to find the treasure. But of course, the island was just too big, and he didn't find it. He went home empty-handed. Okay. So the thing is, had that guy have a knowledge of the complex numbers that I've shown here, in particular rotations between complex numbers, this would have been straightforward. Okay, and let's show you how. So again, let us take the oak, the point for the oak, and then for the pine. Okay, so the thing is, so you draw a line between them, okay, between the oak and a pine. So you only have 2 points, so it defines a unique straight line. In the midway here, right here, call this your origin, and so the line, the axis intersecting the oak and the pine, call this your real axis. Okay, and then the axis in between them, this one, call this the imaginary axis. All right, and you know, let's say we don't have a meter stick or something, so let's call the distance from the oak to our reference point as the unit distance. So let's call it 1. So from here to here it's -1, from here to here it's +1. Okay, we don't know the distance of the gallows. It could be anywhere, but now we have an Argand plane. So any arbitrary location, we don't know the location of the gallows, but let's say it's somewhere here. It's an arbitrary location. We can call it its position as A plus BI, okay? Which, for simplicity, we can call it gamma. That's the rotation of the gallows. Now, let's take the distance, because what you're supposed to do, assuming the gallows is here, is you're supposed to walk from the gallows to the oak, okay? So let's take the distance from the gallows to the oak. And basically, how do you do that? That is just the final position, -1, minus the initial position, so this complex number which we call gamma. So we can simplify that as -1 plus gamma, right? And then next, the distance from the gallows to the pine, this one. So gallows to pine, we can write that as the final point, 1 minus the gallows. Okay, so the instruction is we turn right from after going to the oak, we turn right 90 degrees. So basically this one. Okay, so we are rotating this arrow, which I said that's just a vector. You can think of it as this arrow, you can think of it as this one. Okay, and what you're doing is turning right is equivalent to turning it, rotating it clockwise. Okay, so in other words, if you want to turn right, okay, turn right is equivalent to multiplying it by the because it is equivalent to counterclockwise, we're multiplying it by the number minus I. Okay, so that's the after turning right. But note that 0 is not the reference point. The reference point after turning right is -1, and like I said before, what you do is you add the original number to the reference point in order to find the correct final point. So this is the final point, this is the location of spike 1, and it will be given by negative I plus gamma multiplied by minus 1, and then added to by the reference point, which is negative 1, so this is minus 1. And then for the gallows to the pine, what you do is you will turn left, and again this is equivalent to this arrow. You want to turn left, you're rotating this counterclockwise to this final arrow right here, okay? And what you do is, again, you multiply it by I, so 1 minus gamma multiplied by I, and then you add the reference point, which is 1, okay? Because it's not the reference point is not the origin. And this point right here is spike number 2, okay? And it is said, the note says that the treasure is found at the center, okay, in the middle. So how do you get the center? Well, we just add the complex number representing this point. So that is I 1 plus gamma minus 1, and then the number representing this point, so we add it to I 1 minus gamma plus 1, and you divide it by half because we want to get it halfway. So this minus 1 and plus 1 will cancel. This will give you 1 half 2i, okay, and then I gamma, and then minus I gamma. The fascinating thing is that the gammas will cancel, and this turns out to be I. So in other words, in our diagram right here, the treasure, the halfway point, is exactly at point I, okay? So note that we don't know the location of the gallows, but it doesn't matter because after doing the calculation, the gamma, the location of the gallows, cancels out. So in other words, the location of the treasure I, which is I in this case, should be independent of the position of the gallows, okay? So if you're not convinced, so this is an arbitrary position, but if you're not convinced, try putting it at different positions and then drawing again where the treasure is. You'll always find that it is located at point I, okay? So had the guy who went there first known this method, he would have gotten the treasure, but unfortunately he doesn't know anything about complex numbers, okay? So these are just a few things that you can do when you have the power of complex numbers, all right? So I hope you've learned something new today, and I'll see you again in the next video. Thank you for watching.